So here's the experimental setup for Faraday's laws of electromagnetic induction demonstration. So we have two solenoidal coils, made from insulated copper coils. As you can see, there are many turns actually, many number of turns. I guess about 400 or 500 turns each. And one is connected to the galvanometer. It's called galvanometer. It measures the current, very tiny current, very sensitive galvanometer. The other coil is connected to the power supply. And so you can see these two coils are not physically connected, right? They are not physically touched. So, but from electromagnetic induction, what we expect is, so when I turn the switch on, let's see what's going to happen. So if I turn the switch on, right, let's see what's going to happen. As you can see, right, it actually shows some deflection, tiny current induction on one side. But when I turn the switch on, immediately after I turn the switch on, it goes to the opposite side, and that's because of the electromagnetic induction, right? So because when you turn the switch on this coil, it changes the flux, right, around it, and the changing flux will induce the current on the neighboring coil, and that is recorded by this galvanometer, right? So let me show you one more time. So when I see, you see tiny deflection, right? But if I bring this close, still they are physically insulated, right? But still, now you expect more deflection. See here. So one side, but when I turn the switch off, you see deflection in opposite direction. That's what we expect. Here's the Lenz law demonstration. So this is a tiny magnet, a cylindrical magnet, and this is an aluminum tube. So as you can see, if I drop it, right, it won't be free fall. It takes some time. The speed has significantly slows down, and it's because of the Lenz's law, right? Because Lenz's law says as the magnet falls, it induces some tiny current on this aluminum tube, and this induced EMF, right? Induced voltage, induced EMF should oppose the change in flux, and that's why it's slowing down actually. And you can do it with a copper tube as well, because there's no attraction, right? So you can check with the copper tube as well. It's same, right? It slows down significantly, and that's because of the Lenz's law.